So for those of you who are working on moving robots around remotely, this might be inspiration. That's what they need. They need to be able to have robots that will go in there and, be able to be controlled remotely and do things that humans could do. Oops. Okay, well, let's go ahead and get started. So I left off last time talking about introducing data flow models, and just as motivation, we looked at the problems dealing with concurrent systems using threads and the extreme difficulty in being able to validate those designs and understand the designs. And so what we'd like to do is give you a sense that those are not the threads are not your only option for dealing with concurrency. That you can use mechanisms that are much more easily understood, easily analyzed. They can be implemented. These mechanisms can be implemented using threads, and typically are implemented using threads. But the distinction is that that the people who implement these mechanisms are experts, not application engineers. They're experts in the concurrency model, the model of computation, and then the people who use the model of computation then are experts in the application domain, robotics or communication systems or other embedded system applications. Okay, and they don't. So the goal is to create infrastructure where people don't get tripped up as much by errors that can occur. So I think one of our goals in giving you experience in the lab with 3 levels of programming of embedded systems, which is the bare iron level, where you're just writing C code that runs on a microcontroller, the RTOS level, where you're writing C code that runs under the control of an operating system on the PowerPC, for example, on the SB Rio, and then at the model-based design level, using LabVIEW as the way of architecting your programs. I think of those, there's aspects at all 3 levels that are relatively immature. In some sense, as far as the history of the technology development, probably there's a long history, obviously, of people doing stuff at bare iron level and at the RTOS level. I think that the model-based design level is newer, and the tools are less mature, and I think will probably evolve a lot more, during your careers than the other 2 levels. But I'm quite optimistic that they will prove to be quite useful in the long run. Okay, so LabVIEW in particular, which you've got experience with in the lab, uses a data flow model, but it uses a particular kind of data flow model, which is homogeneous synchronous data flow. So the idea here is that every block requires inputs to be available at all of its input ports, exactly one chunk of data, whatever the data type is, and it executes and then will produce one chunk of data on its output. And then LabVIEW overlays on top of this structuring mechanism where you can create conditionals where, for example, you have 2 alternative sub-block diagrams, sub-VIs as they call them in LabVIEW, and you execute one or the other depending on a Boolean control. Or you can have iterative constructs where you execute sub-VI repeatedly. But those control mechanisms are really, in a sense, based on this homogeneous synchronous data flow model, because everything is ultimately reduces to these blocks that produce and consume a single token. So a simple generalization of that is called synchronous data flow, or by some people it's called static data flow. And the difference here is simply that a block is able to consume or produce some fixed integer number of tokens when it executes. So there's a precondition for executing the block, which is that there be m tokens available in a buffer at its input, and perhaps n tokens available at a buffer at a different input, and that when it fires, it'll produce some p tokens on its output. Now, this is fundamentally no more expressive than homogeneous synchronous data flow, at least if you restrict it to consistent models, and we'll look at exactly what that means shortly. Dynamic data flow extends this further by allowing blocks that do data-dependent consumption and production of tokens. So two very simple versions of such blocks are a select, which will be given a Boolean input on this input port and will then require a token on one of these two other input ports in order to then just send that token to its output. And the switch does the complement. It takes a token at this input port and a Boolean valued control token here, and it'll route this token to one of the two outputs depending on the value of the Boolean. Okay. So last time I talked about this spectrum example, and just to remind you of a very simple abstracted version of it, assumes that we've got a sensor, a component that's wrapping a sensor, feeding a component that's, feeding data to a component that's wrapping an actuator. So it could be an audio signal, for example. In the spectrum example, this guy was collecting audio samples. This guy might be playing back the audio samples or transmitting them into a network or something like that. This is doing spectral analysis or some other computation that is more long running. Okay? And in particular, the model here fits the synchronous data flow or static data flow scenario pretty well, because the assumption is that in order to do this analysis in this red block, you need some window on the data. So you want to accumulate a bunch of data. So if you were to naively schedule these things under the assumption, say, that the C block requires 8 tokens from A in order to execute, then you could end up with a schedule like the one that is depicted down below, where you have alternating blue and green firings and then this long-running computation. And as we discussed last time, that has a disadvantage that it introduces pause times in what might be a time-critical operation here. Okay, it will introduce latency. It would require you to do additional audio buffering, for example, if it's an audio signal or if it's some other control signal. So what can we do that would be better? Well, there's a number of things we could do. One thing we could do is simply make things a little bit more uniform in time by constructing a schedule like this. Okay, so in a sense, this minimizes the latency between A and B, because with this schedule, B will fire as early as possible after A fires, irrespective of what C is doing. Okay? But the disadvantage of this schedule is that it leads to rather poor processor utilization, right? In fact, this long-running computation ends up determining the overall throughput that's possible with your application. So that's not a particularly attractive solution. So an alternative is to, in fact, exploit multi-threading. Now, I want to emphasize that what we want, again, since some of you came in after I said this before, the idea here is that you want the application designer using the high-level model of computation and understanding the application from the perspective of the data flow behavior. The underlying implementation may use threads, and it may use threads with interlocks and mutual exclusion and priorities and all that nasty stuff that leads to scheduling anomalies, deadlocks, and so on. But the goal is that the threaded implementation is done by an expert in threads. and not by the expert in the application domain, right? Who is, you don't want people in the application domain to have to become experts in threads because it's a rather difficult thing to master, okay? But you can implement this using threads as follows, where you would have, in this case, two threads, one that would handle the execution of C, one that would handle the execution of A and B. Why don't I put A and B in separate threads? Why not have three threads? Yeah, Apurva. Right, I need to finish A before I do B, so it would seem like there wouldn't really be any particular advantage to using a separate thread. However, if this is genuinely data flow, okay, there's no reason why you couldn't pipeline this. So a second execution of A could be occurring simultaneously with the first execution of B. Okay, so in particular, if you had hardware resources that could exploit multi-threading using, for example, multiple cores, there would be an advantage potentially to putting the blue and the green into separate threads. Okay, now you would have to trade this off against the overhead that is introduced by the inter-thread communication, right? If A is executing in one thread and B is executing in a separate thread, and they're communicating, then you're going to need some form of interlocks in that communication. That's going to cost you something in overhead, okay? And you need to trade that off against the benefits you get from splitting it up into multiple threads, okay? These are the kinds of questions that come up when you use when you construct implementations like this. I'm going to walk you through a rather clever implementation of a multi-threaded implementation of this style of models that is actually realized in Simulink, which is, how many of you have used Simulink? Okay, so it's sort of LabVIEW-like for those of you who haven't, but not really. I mean, it actually has a different model of computation, fairly significantly different. But it has code generators that use a rather clever technique that I'm going to show you that under the hood produce all of the interlocking code and generate the priorities for threads, and the implementation provides certain guarantees about performance that are really fairly attractive, and it also uses priorities in a clever way to reduce the overhead that's involved in the inter-thread communication. Okay. All right. So why in this picture have I given the red thread lower priority than the blue-green thread? Yeah. Right. Right. We probably don't want the long-running process blocking progress in the short-running processes, and in particular, if you remember this scenario, I kind of assumed that B was time critical, right? So suppose that, for example, this is part of a control loop, or it's part of a interactive audio system. Suppose it's a music system, right? This is a microphone. You're doing some processing on microphone data and synthesizing sound that maybe as an accompaniment to the musician or something like that. Latency matters a lot in that scenario, and you want to reduce the latency as much as possible. And in particular, you don't want jitter, you don't want long pause times, you don't want to use Java where you might pause for a third of a second to do garbage collection. Okay, these are issues that you have to be concerned about, right? So if you have a less time critical task or a long running task, you generally want to give it lower priority. Now, notice that I didn't use a rate monotonic argument here. I used kind of a hand wavy argument. You could use a rate monotonic argument, right? In particular, if C executes once for every 8 input tokens, then it executes at 1/8 the rate of A and B. So by rate monotonic principles, I should give it lower priority. but it may not have any time criticality at all, right? So even that argument, right, the fact that it's executing at that rate, it's a little bit hand-wavy even then, okay? So this is one of the problems with priorities, is that, you know, it's often hard to completely defend your choice of priorities, which is why, you know, you'd like to have them systematically synthesized and not be really something that the user defines. What you'd like is for the user to simply see this as a data flow model, and then there's an underlying implementation that tries to optimize for latency. Okay? All right, so in steady state, as this thing repeatedly executes on a single processor, we could get a schedule like this, okay, and it will in fact be following rate monotonic principles. Of course, this schedule is kind of idealized because it assumes that the execution time of this red block is exactly 8 times the execution times of each of the blue and the green. In general, you don't have a lot of control over the execution time of software. It can be variable. You might be able to bound it, okay, but you don't have a lot of control over it. So you've got to, if you have a multi-threaded implementation, you have to synthesize software that will work correctly irrespective of what the execution times actually end up being, okay? So in particular, if the red block happens to execute longer than expected, you should delay the execution of these guys, or should you? Depends on what green is doing, yeah, but notice that red is not producing any data that is used by green or blue, right? So why would I want to do this delaying? Yeah, right. So if I'm buffering data for C that comes from A, all right? Presumably, this next execution of A is going to provide some data. I'm either going to have to provide a longer buffer. If it executes early, I'm not done with the data yet, okay? In fact, I don't know when in this execution of red it's going to read its input buffers. It could read them anywhere, okay? So I have to assume that it'll read them as late as possible. That's the worst case scenario, all right? So I don't want to overwrite the buffers. So if I were to execute blue immediately, I would have to provide a longer buffer. How much longer? Well, suppose that red chronically runs long. It always runs long. Then how long does the buffer need to be? Infinite, right? Because you'll just get a slowly accumulating, maybe not so slowly, but a slowly accumulating unconsumed buffers. Basically, red can't keep up with blue and green, okay? And no matter what scheme you use to allocate buffers, you're going to run out of memory and your program's going to crash, okay? So that's an argument for doing this interlock here, where at the conclusion of the execution of red has to flip a bit in a semaphore, and that semaphore has to be used to enable the next execution of blue. So this is where you want, you want a back-end compiler generating the code that does this. You don't want the application programmer to have to write this. Right? The application programmer should focus on the logic of, the music application or whatever it is that they're doing. Okay, similarly, if red finishes early, you don't want it to immediately start its next execution because the data that it needs isn't there yet. Okay, so there needs to be another interlock where once there is enough data for red to execute, you flip a bit in a semaphore and that enables the next execution of red. Okay, so with these two interlocks, you get determinacy. Now, what if green executes long? Do I need an interlock? Apparently not, right? It's not shown in the picture. Why not? Why do I not care if green executes long? Does it say it right there? Brilliant. How did you come up with that? Okay. Yeah, it gives you the answer right there. The blue-green thread has higher priority, right? Therefore, red's not going to get a chance to do its thing. Neither is the next execution of blue is not going to get a chance to do its thing because it's executing in the same thread. Okay? So if green runs long, both red and blue are blocked. And consequently, you don't need a semaphore or an interlock to ensure that. You really don't want application programmers to have to do that kind of reasoning. Okay? You really don't. You want that to be part of a compiler. So this is what Simulink does, okay? And in fact, Simulink actually gets rid of a bunch of these interlocks by leveraging priorities. So this is what Simulink looks like if you haven't used it. And in this particular scenario, if we're using a Simulink model, Simulink is not a synchronous data flow model. In fact, it's strictly not a data flow model at all. It's actually a time-triggered model, okay? And like LabVIEW, the buffers that are used to communicate between blocks can only contain one token of data. That's all they hold. And the model of computation is that there's a notion of time, and at each time, logical time in the system time, simulation time, every wire has a value, okay? So if you want to accumulate 8 samples and present them to this red block, then and execute the red block at 1/8 the rate. The way you do this in Simulink is you use a block called a ring buffer, and a ring buffer will execute as fast as A and B, okay? And each time it executes, it collects one new value, and then it outputs a vector. And the vector is simply the 8 most recent values it's seen. Okay, so it's a new data type, but on each time it fires, it outputs a vector of 8. Then, in addition, you can set what are called sample times in Simulink for each of these blocks, which simply says, it specifies how often they should execute. So it's the time, it's the sample period. I don't know why they called it sample time, but it's sample period. Okay, and if you set the sample time of this red block to 8, then it will execute 1/8 as often as the others. So how will this work in a multi-threaded context? Well, first of all, suppose that C is executing in a different thread from the rest of this, okay? On every execution of these 3 blocks are all executing at the same rate, okay? So we could put them in their own thread and execute A, then either the ring buffer or B in the ring buffer in either order, okay? Probably if B is an actuator, we want to execute B first, then the ring buffer. All right, if C is executing in another thread, we have a problem. Right? Because C may be long running. It may stretch out over more than one execution of the ring buffer. Its inputs could change halfway through its execution. And we don't know when it's going to read its inputs in its execution. So we can't allow its inputs to change halfway through an execution. So what you do in Simulink is you put in another block called a zero-order hold. Okay? And the zero-order hold runs at the rate of the red block. Okay? So it'll run at 1/8 the rate of the other blocks. And each time it runs, it simply takes a look at the vector of 8 inputs and produces those on the output, and then just holds that output because it doesn't execute again for another 8 time units. Okay? So as a consequence, because of that zero-order hold, this red block is able to read its input anytime during its execution. Now, the clever thing that they do when they generate code for this is that they execute the zero-order hold at the rate, in the high priority thread, not in the low priority thread, even though it is actually executing at the lower rate. So rate monotonic principles would suggest that the zero-order hold should execute in the low priority thread. Okay? However, if you execute the zero-order hold in the high priority thread, then you don't need an interlock. You get rid of one of the interlocks. Okay? Does everybody see why? The issue here is that as soon as the zero-order hold becomes enabled, okay, meaning that the ring buffer has executed 8 times, the zero-order hold becomes enabled, the zero-order hold will execute, not the red block, because the zero-order hold is in the high-priority thread. As a consequence, it'll grab a snapshot of its input, present it on its output, and it's assured that the red won't have read it prematurely because it's in fact preempting the red. Okay? So you're using priorities here to prevent the zero-order hold from looking at its input at a random time, okay, which is what would happen without an interlock. Suppose you execute suppose you generate code like this without an interlock, and you execute it on a multi-core processor. Will it work? What could go wrong on a multi-core processor? If we're executing on a multi-core processor and we've got 2 threads, one with high priority and one with low priority, which one runs? Both of them, right? On a multi-core processor, your priority says if you have a choice between 2 threads, pick the high priority one, right? But if you have the capacity to execute both, execute both. That's what a typical scheduler would do. Okay? So there's a trickiness here, which is that if you write code that carefully takes advantage of this avoidance of an interlock, that code's not portable. Okay? The same code will fail on a multi-core processor and will introduce non-deterministic behavior. Okay? This is another reason that you want this to be part of the compiler infrastructure and not part of the application program. Yeah?
When you said something like precedence, like you say zero-order hold has to complete both edges.
Yes, so that would be putting in an interlock between the zero-order hold and the thread. So the way you would implement that is that upon execution of the zero-order hold, you would set a semaphore saying zero-order hold has executed, and then in thread 2, at the beginning of each execution of the red, you would block on that semaphore, right? But the overhead of doing that is considerable, so if you can get rid of the overhead, you'd like to, right? But this is an argument for putting this in a compiler infrastructure and not in an application program, because the compiler infrastructure can handle targeting multiple machines, right? A single core or a multi-core machine would generate different code, right? As opposed to having a situation where you've got an application program, you upgrade your processor, and all of a sudden it's failing in mysterious ways and you have no idea why, right? Okay. So I mentioned that Simulink is not truly a data flow model, and the fact that you need this zero-order hold is a consequence of that, right? There's no buffering in Simulink. There's just at every time the buffers have a value. Here's a slightly more complicated scenario where you have two blocks, red and green, that execute at a high rate, and a red block in between them that executes at a low rate. Okay, so the executions of C depend now on data produced by the red block. If we were to produce a sequential schedule, it could look like this, where you have, say, assume that, for example, that the red block requires 4 data values from A. Then you could have 4 executions of the blue, 1 execution of the red, 4 executions of the green. If the blue and the green are sensor and actuator, this is going to create a lot of jitter. Okay, your sensor is reading a bunch of data, then not reading a bunch of data, then reading a bunch of data. Okay, and similarly, your actuator is doing the same thing. Now, you could smooth that out with buffering, but that's going to increase your latency. So the question is, what could you do to schedule this in such a way that you don't increase the latency? So again, you could use a multi-threaded solution where in thread 1 you execute the blue and the green, okay? But you do it as follows. Using interlocks, you ensure that the red doesn't execute until you've done 4 executions of the blue, at which point red becomes enabled in a lower priority thread. You continue to execute the blue, preempting the red. Okay, so you read your sensor data at regular rates. As soon as the green becomes enabled, you execute it in the high priority thread. Okay, so this is one scheme that you could use to execute this kind of model. And in Simulink, this requires an additional block called a delay. And why do you think that's required? Let's see, is the answer given right here? Not in any way that's understandable. So can anyone tell me, why do you think? Well, first of all, what is a delay? Right, okay, so what the delay does is each time it executes, it produces on its output the current state, which is simply whatever it read on its input on the previous execution. Okay, and then it reads its input state and records it for future use. Okay. So can someone articulate for me why we need the delay? Not that hard. Come on, you guys can figure it out. Yeah.
Could it be because we integrated the red finishes?
Yeah. It's not so much that we don't know when red is finished, it's that we don't know when red produces its output. Right? Red could produce its output anytime during its execution. It doesn't. Producing the output doesn't have to be the last thing it does. Okay. Suppose that it produces its output right there. Okay. Then if I didn't have the delay, what would happen is that output would overwrite the previous values, which is what the green is reading. Okay. So you don't want to overwrite previous values, which is the reason you put in that delay. And again, Simulink has this clever technique that even though the delay runs at the low rate, they run it in the high priority thread, and that avoids an interlock, but again creates code that will not work on a multi-core machine. Okay? So part of my goal here was to give you a sense of, that there's interesting problems in taking these sort of high-level models and synthesizing embedded code from them. There's been many efforts that take these high-level models and synthesize hardware. Okay, on FPGAs or even ASICs, those also have very interesting problems, optimization issues and questions. Yeah?
Also run delay just before execution of C and instructions.
Could run I'm sorry, the delay could run just before the execution of C. That's right. Sorry?
Between the blue and green.
Between the blue and the green. Yes, that would work fine. Yes, that's correct. Yeah. Right. Yeah, it's a bit of a mind bend, and you know the way if you read the manual, what it tells you is that whenever you're going from a high sample rate to a low sample rate block, I mean, which means going from a low sample time to a high sample time block, use a zero order hold. Whenever you go from a high sample time to a low sample time, use a delay. And so engineers, you know, write this on a sticky note and paste it on their monitor, and they don't have any idea why, which suggests something a little bit wrong with the model of computation, in my opinion. But because it's a bit of a mind bend, and you can't understand why unless you understand this multi-threaded implementation. Okay, so what the zero order hold does is both of these execute at the low rate. Okay, so they're going to execute. This is going to execute once for every 4 executions of this. Okay, and what it's going to do is simply then take a snapshot of its input and hold that value for the entire sample time that this red block executes. Okay, so that way red can read its input data anytime during its execution. This is not a very data flow view of the world. Okay, in a data flow view of the world, you read your data when you've got a new token. Okay, and it's taken care of for you that doesn't get overwritten before you've read it. So in a sense, the fact that Simulink is not data flow sort of rears its ugly head here by having to have these post-its on your monitor that remind you to put in the zero order hold and the delay in the appropriate places. It also, by the way, what should you do if you have a block with a sample time 2 feeding a block with a sample time 3? I would suggest panicking would be a reasonable reaction. In fact, what will happen is if you try to do that in Simulink in this multitasking mode, you'll get an error message. It's a mysterious error message that says you can't do that. And if you turn off multitasking, you can do it. There's a kind of a flaw in the model of computation again. You're right. The model of computation shouldn't depend on the implementation, but it does in this case. Right? If you implement it one way, you have to have this block in there. If you implement it another way, you don't. So this technique is cute, but not. I mean, it sort of, I think, highlights somewhat that this field is really not so mature. Right? This technique is pretty widely used, actually. In fact, it's probably one of the most widely used model-based design techniques for embedded software. Automotive companies use this to generate embedded code for engine controllers and things like that. Okay. So, all right. So let me. Why don't we take a 3-minute break here, and then I'm going to switch to talking about synchronous data flow models. I guess we haven't posted a solution, so all right, I'll take it.
I thought it was just
Yeah.
projects and I forgot about it.
Yeah, it's okay.
Smack. Since I don't go to lab.
You'd have to ask Kevin for them. They're in the lab. If you get in the lab, you can find them. The lab is 119, Corey. Yeah, because there's a stack of them there. It's card key access, so.
They forgot to take it from me, so I can probably.
Okay.
That way, like, they like, yeah, I bet. Yeah, exactly. It's like, you know,
Like, that would drop to. That like.
yeah, it's gonna be fun. Yeah.
And we're tied with the race, so.
Yeah.
We're still the best.
Yeah. I mean, well, at the same time, it might be an estimation, but if we can use if you're offended, like yeah. No. Some May, then it gets really hot. Yeah.
Okay. According to my watch, that was 3 minutes. So. Does anybody have any questions so far about this? All right, so the next thing I'm going to talk about is a topic that's actually fairly dear to my heart because it was the major part of my PhD thesis. So maybe it'll give you a sense also of what a PhD thesis looks like when you work on this kind of area. So let's see, this is just a review of what we've looked at. So in particular, what I'm going to focus on next is true data flow models that are a little bit richer than the LabVIEW model in the sense of allowing for multiple consumption and production of tokens, and are genuinely data flow, unlike Simulink, which is more of a time-based model. So the notion is now very simple, that if you have a computation, you specify firing rules, which are integer values on the input ports that specify how many tokens you need in order to be able to perform the computation, fire the actor, as the terminology goes. And then you also specify how many tokens are going to get produced upon firing that actor. Okay? So I should tell you, here is a list of variants of data flow and the dates in which they were introduced. And the one that I'm talking about is, from 86, basically. There's a lot of variants, and many of them are really quite interesting, and it's a kind of an ongoing area. Okay, so synchronous data flow. If you have an actor that produces P tokens, P for produced, feeding an actor that consumes C tokens, C for consumed, the key idea is that you would like to maintain this system in balance so that the number of tokens produced equals the number of tokens consumed. Straightforward concept. Okay, what that means is that if you let Q sub A be the number of firings of actor A and Q sub B be the number of firings of actor B, then you would like Q sub A times the production value for actor A to equal Q sub B times the consumption value for actor C. Actor B, that's a typo. That should be a B. And that should be an A. Okay? So hopefully, despite the typos, you can see it's a trivial thing, right? You want the total number of tokens produced to equal the total number of tokens consumed. Now, of course, in a data flow model like this, you may have an infinite number of executions. Yeah?
Wouldn't that be right? P of C is the P of output of the C.
You're right. Yes, the C here means the connection. Yeah. That's the notation that's being used here. So actually, it's not so bad. Yeah, so P sub C is the number of tokens produced on connection C, and C sub C is the number of tokens consumed on connection C. Okay? Or consumed from connection C. Yeah. Okay. So the system is going to be in balance if this is true. But now, of course, the problem is, how many times should we execute A and how many times should we execute B? Well, potentially infinite, in which case, I guess if you set Q sub A to infinity and Q sub B to infinity, then the equation is trivially satisfied. You could also trivially satisfy it by not executing either actor at all, right? Set the firings to 0. But those are probably not good choices, right? So in particular, the infinite executions doesn't really tell you anything, and the 0 executions doesn't accomplish anything. So we would like to do something a little bit different. Now, for a simple 2-actor system, things are kind of boring. But when you start to get a network of these things, it gets a lot more interesting. Okay? So in particular, suppose that actor 1 produces 1 token on its top port and 2 on its bottom port. Actor 2 consumes 1 from this port, produces 2 here. And actor 3 consumes 1 from each input port. Okay? So you can write down balance equations for each of the 3 connections, and we can collect those balance equations into matrix form as follows. So this gamma matrix says that has a row for each connection. Okay, so there's 3 rows because there are 3 connections, and it has a column for each actor. And at the point in the matrix, you just put an integer that says, how many tokens does this actor produce on this connection? So it produces, actor 1 produces 1 on connection 1, and actor 2 consumes 1 on connector 1. So we use a negative number for consumption, a positive number for production. We collect the number of firings of the actors into a vector, and we just write down a matrix equation then that says that gamma times q should equal the 0 vector. And that's all the balance equations collected.
So
yeah.
what's the consequence of the trivial solution to that equation?
Right, so there's 2 trivial solutions to this, right? One is you set q to 0, which means you don't do any computation at all. And the other one is you set q to infinity, which says that you execute everything an infinite number of times. And that may actually be a pretty reasonable answer. You may want to execute it an infinite number of times, but you haven't learned anything about the system. Okay, so I'm going to show you that you can learn something about the system from these balance equations, and you can use it to optimize your schedules. You can use it to decide how big your buffers need to be. And you can use it to analyze systems for deadlock. Okay? So for this particular example here, if we have A producing 1 token every time it fires, C consuming 8, B consuming 1, then the topology matrix, as it's called, will look like this. Okay? There's only two connections here, in effect. There's a connection from A to C and a connection from A to B. Okay, so there's 2 rows in the matrix. There's 3 actors, so there are 3 columns in the matrix. Okay, so here's a non-trivial solution to the balance equations for the previous example that I gave. Okay, this non-trivial solution says that if you fire actor 1 once, actor 2 once, and actor 3 twice, the system will be in balance. Okay? So in particular, this will be satisfied. And if you just look at the numbers, that's kind of obvious, right? Because actor 2 is going to produce 2 tokens each time it fires. Actor 3 consumes 1, so actor 3 needs to fire twice as often as actor 2. Actor 2 needs to fire the same number of times as actor 1. Okay? And this connection is kept in balance if you do those firings. Okay? But there's lots of other solutions. As I mentioned, the 0 solution. I could also keep the system in balance by firing actors 1 twice, actor 2 twice, actor 3 4 times. I could give a negative solution to the balance equations. I could give a rational or an irrational solution to the balance equations, okay? But pi as a number of firings is not a very useful answer, and a negative number is not a very useful answer, okay? So the first theorem, in a sense, is that for well-behaved models, which I'll define in a minute, there is a unique least positive integer solution, okay, where every element in the solution is a positive number, not 0. Okay. So what is well behaved? Well, first of all, let me just kind of outline for you how you would go about showing this. The least positive integer solution relies on the fact that the production and consumption numbers are integers, and therefore you can always find a rational solution. If you can find a solution at all to the system of equations, you can find a rational solution, okay? And if you can find a rational solution, you can find a least common multiple of all of the denominators and therefore find an integer solution, okay? The fact that there is a least integer solution and that it's unique is not quite so trivial, okay? But the fact that there is an integer solution is pretty trivial.
With the least positive integer solution, then so the least positive integer solution, implies that you have that vector, and then does the fact that it's unique imply that all of the other solutions lie along the line defined by a constant multiplication?
Yeah.
Or could there be some other one that's some other line?
Yeah, so that's good insight. So all of these solutions are in fact scaling of the same vector. Okay, if you treat this as a vector in 3-dimensional space, all of these solutions are just a scale factor multiplied by that vector. And so the only thing, the interesting thing is, first of all, that the solution space is 1-dimensional, okay? Assuming there is a solution. I'll show you in a minute there may not be a solution, okay? And that somewhere along the solution space there is a rational solution, okay? And that as a consequence there is a least integer solution. And moreover, that there's a solution where all of the entries in the vector have the same sign, okay? By the way, this is very typical of kind of a graph theoretic algorithm, or graph theoretic technique. These kinds of adjacency matrices are used in graph theory all the time. Okay? So an adjacency matrix means, basically rows for connections, columns for nodes, and some information about connectivity in the entries. Okay. So the rank of a matrix is defined to be the number of linearly independent rows and columns. Okay? If you've taken Math 54, they covered this in Math 54, right? So, yeah. So pop quiz, Math 54, what does the rank of gamma need to be to ensure that there is a unique solution? Sorry? Full rank, yeah. Right? If it's less than full rank, then your solution space will be multidimensional. Okay. So, in particular, if A is the number of actors, and oh, by the way, one key assumption that I'm going to make henceforth is that the graph is connected. So, in particular, there's no cluster of actors that don't communicate at all with some other cluster of actors. If I did have that, I would just separate those into two connected graphs and treat them independently. Okay? Why could I treat them independently? Well, the data flow model doesn't imply any constraints then on the execution of these two connected submodels, right? Because there's no communication between them. So I can separate the problem into two problems. Okay, so if we assume that we have a connected graph, then if A is the number of actors in the connected graph, then that is also equal to the number of columns in this matrix. Okay? If the model is a spanning tree, meaning that there are barely enough connections to make it connected, meaning that if I remove any connection, it becomes a disconnected graph. Okay? Then there will be exactly A minus 1 columns, because there's A minus 1 connections, and there's A minus 1 rows, because there's one row for every connection, one row for every actor. Okay, if I have a spanning tree, the number of connections is exactly equal to the number of actors minus 1. Okay, that's the minimum number of connections that can yield a spanning tree. Okay, so so in this case, the rank of the matrix will in fact equal A minus 1. Okay, and that's a key theorem. Okay, but that is a full rank matrix, in fact, because that's as high as the rank could possibly be. Why can't the rank be A? Doesn't have enough rows, right? It can't have A linearly independent rows because it only has A minus 1 rows. A minus 1 rows. There's one row per connection. Yeah. This is backwards. It has A columns and A minus 1 rows. Okay? Okay. Here, let's actually go. Let me do this in a slightly simpler way. Okay? Let's create a variant of the previous model. In particular, what I've done is changed the value here used to be a 2. Okay? Now it's a 1. So when actor 2 fires, it's going to produce a single token. Okay? So the resulting topology matrix now is this one. Okay? What's interesting about this model? 0 is the only solution, right? This is in fact a non-singular matrix. Okay? 0 is going to be the only solution to the balance equations. And if you look at this model, you can tell, actually, that would be the case, right? Because how could we fire this thing? Well, if we fire this actor, it's going to produce 1 token here and 2 tokens here. That enables 1 firing of this, which will produce 1 token. So now we have 1 firing enabled here. We can fire it once, but we're going to have a leftover token here. Okay? So we're not in balance yet. What can we do next? Well, the only thing we can do next is fire 1 again, which is now going to give us 3 tokens on this connection. each time we repeat that process, we get accumulating tokens on this connection. And as a consequence, there is no sequence of firings of these actors that is balanced except to not fire them at all. Okay? Every sequence of firings allowed by the data flow model will result in leftover tokens and an accumulation of leftover tokens. Okay? So the key is that we need for the rank of this matrix to equal the number of actors minus 1. We cannot have it be any bigger than that. Now, this is not a spanning tree. Okay, this graph here. If I remove this connection, I still have a connected graph. Okay? Any spanning tree will yield a non-trivial solution to the balance equations. Okay? But when you have something that's not a spanning tree, you could end up in a situation where you have no solution to the balance equations. So the key idea in synchronous data flow is to declare models that have this property defective. So you simply say, we're not going to allow you to execute those. We call them inconsistent. They cannot be kept in balance. One way to justify that is that if you were to do any unbounded execution of this data flow model, any unbounded execution is going to require an unbounded amount of memory. Okay? Now, here's an interesting sort of fundamental question. If you write a C program, say, let's assume you don't even use malloc, right? So there's no heap, just a plain old C program. Can you tell how much memory it's going to use? Is there any procedure you can follow that will analyze a C program and tell you how much memory it uses? Sorry? If there's no dynamic? Yeah. If there's no dynamic memory allocation, however, you still can't tell because C relies on a stack. There's a stack model, right? Whenever you do a procedure call, you do effectively allocate memory on the stack. Okay? So in order to determine how much memory a C program uses, you have to be able to tell what's going to happen on the stack. How can you tell what happens on the stack? Well, you have to analyze all the procedure calls. What if you have a recursive procedure call that is doing some data-dependent computation to determine whether to do another round of the recursion? Okay? You may not, in fact, be able to tell. You may not be able to put a bound on the stack. Okay? It's a very fundamental result in computer science, due ultimately to Alan Turing, that there is no algorithm that can tell you for an arbitrary C program how much memory it uses. Okay? It's, in fact, Turing showed that question is equivalent to the halting problem, which is that there is no algorithm that for an arbitrary C program can tell you whether the C program halts, meaning it reaches the end of its main. Okay? For synchronous data flow models, however, there is an algorithm that tells you how much memory this uses. Okay? And in particular, that algorithm is hinted at by the difference between this model and the previous model. If you have a consistent model, meaning that there is a non-trivial solution to the balance equations, then the data flow model can execute in a bounded amount of memory. And you can, in fact, determine a minimum on the amount of memory required. So all you have to do to determine whether this data flow model can execute with a bounded amount of memory is determine whether the balance equations have a non-trivial solution. That is an algorithmically solvable problem. Okay? So as a consequence, the memory usage question for a synchronous data flow model is decidable. Okay? There's an algorithmic procedure that given any synchronous data flow model can tell you. What about halting? Well, suppose I have a synchronous data flow model like this, right? Does it halt? So the way to read this is that in order for A to fire, it has an input port. It requires a token here. Okay? When it fires, it'll produce a token here. Similarly for B. B requires an input token here, and when it fires, it'll produce a token there. Sorry?
Can we initialize the wires to be with it?
Can you do what?
Can we initialize the wires to be with it? Otherwise, it
Yeah, so let's assume the wires are not initialized with any initial tokens. Yeah. So it halts immediately, right? This particular synchronous data flow model halts right away, before it does anything, in fact. Reaches the end of the program and bam, it's done. Is it consistent? Is there a non-trivial solution to the balance equations? Yeah. Right? 1, 1. Okay? So the balance equations may help you with the memory problem, but they don't directly help you with the question of deadlock, all right? The halting question. However, in fact, they do. You can use the balance equations to also solve the halting problem for synchronous data flow models. So here's a slightly less trivial example than the previous one. So here the production and consumption numbers are all shown here. This guy requires 4 tokens to execute. The feedback arc is initialized with only 3 tokens, therefore this thing halts also. But it doesn't halt immediately. Okay? In fact, this actor here doesn't have any inputs. As a consequence, it's able to produce tokens whenever. In fact, this program technically doesn't halt, right? Because this actor is always enabled. It can always produce data values. Therefore, you could have an execution here where this actor just infinitely produces data values. However, that execution will require an unbounded amount of memory, right? Because the data values will accumulate on this buffer. Okay? So this is not a deadlock problem. This is where there's only a portion of the model that has deadlocked. Okay? And this model, by the way, is also consistent. So the interesting observation about this model is that it does have an infinite execution that does work, but it has no infinite execution that executes with a bounded amount of memory. Okay? And the reason for that is because of this local deadlock that occurs inside the model. This is different from this situation where this model also has an infinite execution, but it has no bounded memory, infinite execution. But the reason in this case is that the model is inconsistent. Okay, so 2 different reasons, but they manifest themselves into the same problem. Okay, so the question of interest is, given a synchronous data flow diagram, can you prove that there is an infinite execution that uses a bounded amount of memory? Okay? And if you think about it, that's the key question you want to ask if you're trying to do this. You're trying to treat this as a specification for an embedded system. You would like the thing to run forever. It should not stop on its own. It's not okay if your control system stops running at some point. Okay? By the way, this is sort of the opposite of what, in computer science, failure to halt is usually treated as a defect. And in fact, in the theory of computation, all programs that fail to halt are equivalent. Okay? They're all defective. And in this theory, it's exactly the other way around. All programs that halt are defective. And the ones that fail to halt are, in fact, the ones that are doing the right thing. Yeah? Question?
Can you explain how the previous example, how it,
This one?
yeah, how they needed unbounded memory?
So the data flow model is that each of these actors shows what its preconditions are for firing by annotating its input ports with the number of tokens it needs. And I kind of didn't say it explicitly, but this guy has no input ports. Therefore, it's always enabled. It can always fire. As a consequence, I never reach a situation in this graph where there's nothing to fire. There's always something to fire because this guy's always enabled. So, and in fact, it's the only guy that ever becomes enabled. Well, that's not quite true. No. I could fire this guy, and then at that point I could fire this, right, because there's a token available. And I could do that 3 times until I've exhausted these tokens. After that point, the only thing that can fire is this source. But I can just keep firing it, right? So that is an infinite execution. The program doesn't halt. But it consumes an infinite amount of memory.
So why is this one not inconsistent? It seems to me that it was
It's not inconsistent. So in particular, the balance equations have a solution, a non-trivial solution, right? The non-trivial solution is that this guy should execute 4 times, this guy should execute 4 times, and this guy should execute once. And if I can do that, I will keep this system in balance. The problem is that I can't do that because this guy never gets enough tokens. Okay? All right, so the key thing is to give an algorithm that will find an infinite execution that uses a bounded amount of memory. And there's a very simple algorithm for doing this, and then a whole string of PhD theses to create more interesting algorithms, right? But a simple algorithm just says, all right, we keep track in a vector of the sizes of the buffers. So for this example, let's assume that there's no initial tokens on the buffers. And our solution to the balance equations is given here. So for a consistent model, for an inconsistent model, we immediately know that there is no bounded execution. There is no unbounded execution that uses a bounded amount of memory. But for a consistent model, we don't know that immediately. So assume we've got a consistent model, we've got a solution to the balance equations, we've got an initial size of the vectors. We choose a firing that is enabled. In this case, actor 1 is the only one enabled, okay? And we get a new buffer size. So now, if actor 1 fires, this is the contents of the buffer. The first buffer will have 1 token. The second buffer will have 0 tokens. These are the buffer labels. The third buffer will have 2 tokens. And at the same time, we decrement the solution to the balance equations. So we did 1 firing of actor 1 already. So we're not going to fire actor 1 again. Okay? We're going to only allow it to fire this many times. So now we fire actor 2. That's enabled, and we're allowed to fire it because it still hasn't reached the number of firings in the balance equations. We update the buffers again. Okay? We can now fire actor 3, decrement the Q vector again, fire 3 again. When we get the Q vector to 0, we will have the buffers back down to 0. Okay? Why are we assured that the buffers will be 0 again once we get to get to 0 in this Q vector? Right, because the Q vector is the solution to the balance equations. So if I execute the actors that many times, it will bring me in balance. So if the model doesn't have any local deadlocks or global deadlocks, I can complete this procedure and bring Q back to 0. If there is a deadlock in the model, the procedure will block somewhere in this finite number of steps. Okay? And it'll block, the way it'll block is that none of the actors will be enabled, or none of the enabled actors will be allowed to be fired according to the Q vector. Okay? Yeah.
Is it possible if, like,
Interestingly, no. Once is enough. Okay? Once is always enough. And it will always reveal whether there's a deadlock. So the deadlock question becomes decidable. Moreover, it tells us how much memory is needed, because all I have to do is look at the maximum value of each of the buffers in this vector through this procedure, and it tells me exactly how much memory was needed for that buffer. Okay? So I've got a procedure that terminates, that tells me whether the model has an unbounded execution. So if I try to run that procedure on this, it gets blocked immediately. Okay, no big deal. So, yeah. Okay, so I mentioned that there's a lot of follow-on work then that creates more interesting algorithms. So for example, suppose that you want, instead of just, sort of blindly going through this algorithm, you'd like to find a procedure that tells you what the minimum size of the buffers is. What is the least possible buffer size? Okay? That turns out to be a pretty darned interesting problem and very hard to solve. It's solvable in principle. It's a decidable question, but the complexity is high. There's a book on this. Out of that book is a rather cute example, which is due to Tom Parks, who was a PhD student of mine, which is a simple signal processing system that converts compact discs to digital audio tape. Okay? Digital audio tape is an obsolete format, and in fact it went obsolete precisely because of this. Okay? It went obsolete almost immediately because the audio industry set the sample rate of digital audio tapes at 48 kilobits per second. And the sample rate of compact discs is 44.1 kilosamples per second. Okay? So 44.1 versus 48. Now why did they choose 48? Well, they said, oh, we can use this for marketing. It's a higher sample rate. You'll get better quality. That's not why they picked it. Right? If they wanted a better quality, they would have picked twice the sample rate. Right? The reason they picked 48 is because it's very hard to convert a digital signal sampled at 44.1 kilohertz into one sampled at 48 kilohertz and preserve the quality of the signal. It's a very complicated computation. Okay? If you do it in a brute force way, it's enormously computationally expensive. And you get lots of rounding errors in there that will degrade the quality of the sound. So the clever technique to do it is to do a cascade of conversions where you do a 2-to-1 conversion, a 2-to-3 conversion, an 8-to-7 conversion, a 5-to-7 conversion, and then you finally get to that rate. So the meaning here is, let's see, I think actually these numbers are, for some reason, Tom expressed these backwards. What this means is that this data flow actor consumes 1 token and produces 2. This one consumes 3 and produces 2. This one consumes 7 and produces 8. This one consumes 7 and produces 5. And this data flow network yields the minimal integer solution of the balance equations are that this guy fires 147 times, same as this. This one will fire 98 times, this will fire 28 times, this will fire 32 times, and this will fire 160 times. And if you look at the relative sample rates, if this is 44.1, if this is sampling running at 44,100 firings per second, this will do 48,000 firings per second. Okay? So Tom also derived then what the minimum buffer schedule for this is, and this is what the minimum buffer schedule looks like for this particular sequence of firings, for this particular group of actors. And it's completely chaotic. Okay? It's very hard to discern patterns in this sequence of firings. So it's not very structured at all. In order to get this minimum buffer schedule, it seems to require this very unstructured schedule. You can get much more structured schedules, but at the expense of more memory. Okay? And in fact, Tom collaborated with 2 other students of mine, Shuvra Bhattacharya and Jose Pino, and did a complete study of this and looked at what the trade-offs were between schedule size and data size. So the minimum buffer schedule, it turns out to require a very expensive implementation because the schedule is so complex. Okay? If you reduce the schedule size, you can reduce the code size of your implementation, but it costs you more memory on the buffers to do that. Okay? And the best minimum memory schedule is a trade-off between code size and data size. Okay. So interesting optimization problems that arise. Now, just briefly, dynamic data flow, as soon as you introduce switch and select, the problem gets much harder. In fact, it gets provably undecidable. Given a model like this, there is no algorithm that tells you whether there is an unbounded execution that executes with a bounded amount of memory. Okay, just introducing switch and select is enough to make it unbounded, undecidable. Okay, so in fact, another student of mine showed that just introducing switch and select, this was Joe Buck, was enough to make the model Turing complete. Okay, and anyway, that's. But again, there's a lot of interesting things you can do. Even though this is undecidable, turns out a lot of programs actually yield to analysis. It's just you can't have an algorithm that will deal with all programs. You can only have algorithms that will deal with some. Okay, so we'll stop there.